Okay, so welcome everybody. It's a great pleasure to welcome you all to the first night of the meeting, Canonical Computations in Brains and Machines. We're really happy that you're here. We had a great time planning this meeting and have been really excited about the content and became even more excited when we realized the enthusiasm for this topic. When we first published the registration site, we didn't really know how many people would come. It's sort of a new topic to bring neuroscience and AI together, and we were excited to see that the meeting sold out very quickly and has been completely sold out, as many of you probably know, for months at this point. So I was really excited to see how much enthusiasm there is for this topic. Our starting point is we acknowledge that back in the 70s and 80s, neuroscience really had a big influence on the field of AI, and the research that was cutting edge at that time was fundamental in driving the kinds of networks that formed the beginning of that field. But since then, the fields have diverged a lot, and we think it's a good time to bring them back together. So we wanted to take this opportunity to have a conference featuring talks both from neuroscientists and also from people working on AI, both in the academic and in the technology sector, and to bring people from both of those fields together to hopefully lead to fertile conversations, collaborations, and we don't know what will emerge, but we're very excited. So thank you again for being here, and it's my pleasure to introduce the first speaker, David Heeger, who will tell us about ORGaNICs, a theory of working memory in brains and machines. Thank you.
Hi everyone, welcome. As one of the co-organizers and the first speaker, my job is easy. I have to keep to time to set a good example for the other speakers, and I have to set a low bar to make the other speakers look good. I'm confident in my ability to do the second of those two things, okay? Anne will keep me to time. This is brand new work with Wayne Mackey. I actually posted a paper, that manuscript that we've been writing, on arXiv today. Unfortunately, it's not going to be available until Monday, so you don't pull out your laptops and try and download it. It's based on a paper that I published, kind of builds on a paper that I published in the Proceedings of the National Academy last year. I'm going to attempt to bring together three different disciplines. Cognitive psychology, the notion of working memory comes from cognitive psychology. Long short-term memories, or LSTMs, which some of you know about as a tool that's being used for a lot of applications in AI. And I want to take that and implement it in a neurobiological circuit. So this is ambitious. The acronym stands for Oscillatory Recurrent Gated Neural Integrator Circuits, and we'll see all of those words as we go. So first, what is working memory? It's a cognitive process responsible for maintaining and manipulating information. It's what you're doing right now as you listen to me speak. You're combining the information that's coming into your ears now with information that you were presented with some time ago to make sense out of the whole, well, last few seconds or last few minutes. It's known in AI as the problem of long dependencies, that you need to combine information now with information that came before. Here's just a fun little example from language. We have this sentence here: the athlete realized his goals, and you can finish it two different ways, and by finishing it each of these two different ways, you have to go back and reinterpret or disambiguate the meaning of the words that came earlier in the sentence. Now, what's challenging about this, and language is a good example of it, is that I can insert any number of clauses in between, like this sentence, the athlete realized his goals, which were formed during childhood, to qualify for this year's Olympics, either finish it either way. So you might imagine that one way to solve this problem would be just to have a buffer to hold all the information until you get to the end. But given problems like this, in which the input is compositional, you can't really do that. So the idea, both in cognitive psychology and with LSTMs and other recurrent neural nets in AI, is that you carry forward from one instant in time to the next a state, and you update that state as the new information comes in. And what's challenging about that is that you want to keep some information for a long time, and you want to forget other information that's irrelevant. Okay, that's the problem of long-term dependencies. In neuroscience, the concept of working memory has been simplified, I think, way too much. using delayed response tasks, an example of which is a memory-guided Saccade or oculomotor delayed response task, which works like this. If you were a subject in an experiment, you'd be holding fixation on this little white dot in the middle of the screen. A target would be flashed briefly in the periphery. You're not allowed to look at it yet. It disappears. You have to remember its location until the fixation point disappears, and then you make an eye movement to the remembered location. The target reappears. You make a correction, and then move your eyes back to the center for the next trial. Okay? And what decades of research has now shown is that in tasks like this, you find neurons in various areas of the brain, most studied in parietal cortex here and prefrontal cortex up here, that there are neurons that are active during the delay period. Here's the cue, here's the delay, here's the eye movement response. You see this in single neurons in monkey brains. You see this with fMRI in human brains. And this is believed to be the brain's representation of the remembered location of that target while it's not on the screen, but while you still have to remember where it is in order to make the eye movement to it. And there are computational theories of this. Here's one that's particularly influential. The idea is that there are neurons in particular brain areas in which each neuron codes for a different position of eye movement. And during the and so one neuron, say, represents this an eye movement from here to here. Another neuron represents an eye movement from here to here. And if the planned eye movement is over here, then that neuron's going to respond the most. And neurons that code for nearby positions will respond a little bit less. And neurons that code for positions far away from that won't respond at all. And that's what you're seeing here in this simulation. This is the location that each simulated neuron likes the best. Here's the cue. Here's the delay period response. You see a bump of activity that's centered here and falls off on either side until the simulated eye movement is made at the end. Okay? Now, what's wrong with that? Well, I think two things. One is that the concept of working memory involves both maintenance and manipulation, and that's only about maintenance. There's no manipulation of information. There's no combining of information in any even simple way over time. The second problem is an experimental observation, which is that you can even see a little bit of right here, that this doesn't look just like flat, sustained delay period activity. There are bumps and wiggles and modulations, and sometimes it looks actually pretty complicated, the way that some of these neurons respond during these delay periods. Sometimes they go up, other ones go down, other ones kind of disappear and recover again. And so there's something missing from that kind of computational description of what the neurons do. And I think that these two things are fundamentally linked with one another, that what this circuitry is set up to do is to do manipulations, and we're giving it an exceedingly simple task so that all it needs to do is do maintenance, right? And it's doing that with circuitry that is inherently built to kind of have things change over time. Okay? And so we're kind of under-constraining the way that it behaves. Now, in AI, there's a whole piece of machinery that's been built up over the last 20 years that originally was borrowed from neuroscience in the form of leaky neural integrators, recurrent neural nets, called these long short-term memory networks, or LSTMs. I think actually it's a terrible name. Not only is it an oxymoron, but in psychology, short-term memory means only maintenance. That's the term in psychology that's used for maintenance without manipulation. And LSTMs are all about manipulation. That's the whole point. They do amazing things. You can take a look at these at a couple of popular blogs that are out there. Even people who program these things up every day are kind of shocked and surprised at the kind of problems that they can solve. And the key idea in an LSTM is that is gating of information. So there are two kinds of gates. One is a gate that goes on or off to decide which information to bring in, and another is a gate that goes on or off to decide which information to forget. And those gates are applied separately to each neuron or each unit in the LSTM. We're actually going to talk about neurons, but here it's just units. They're kind of complicated, though, so it's not at all obvious how to map this onto neurobiology. So that's the game plan, is to build a variant of an LSTM that I'm calling these ORGaNICs that map neatly onto neurobiology, that do maintenance and manipulation, and more. If there's if Anne doesn't throw me off the stage before I get to that. So what's a good starting point? A starting point is a simple linear neural network, leaky integrator. Here's a diagram of one. There's 2 input neurons. There's a set of 8 output neurons. Each of these output neurons computes a weighted sum of the input neurons. These solid lines mean positive weights. The dashed lines mean negative weights. And in addition, each output neuron provides recurrent input to itself and its neighbor. So you see this guy right here sends an output out, also gives itself recurrent excitation. It gets recurrent excitation from this neighbor and from that neighbor, and recurrent inhibition from that neighbor. X's are the inputs. Y's are the outputs. This matrix W with the subscript ZX is what we call the encoding or embedding matrix. It's just we compute that this is just a weighted, the input drive here is a weighted sum of the inputs. This thing here is the recurrent weight matrix. The recurrent drive is a weighted sum of the outputs. So you can write it this way if you can see it. The change in the responses over time depends on an input drive and a recurrent drive. The input drive is a weighted sum of the input. The recurrent drive is a weighted sum of the output. And there's this number here, lambda, that determines the trade-off between how much input drive there is and how much recurrent drive there is. We'll see in a minute that that actually turns out to be, well, in fact, in the next slide, the effective time constant. Okay? So here's some examples, a simple example in which we have only one neuron. So now this is no longer a vector, but just a scalar number, the change in that response over time. Here's the input. And here's a set of outputs you get for different choices of lambda. If I choose lambda to be a large number close to 1, then this term dominates and that term goes away, and the input and the output, plotted down here, pretty much follows the input. But it also goes away as soon as the input goes off, so it has no maintenance. Okay? If instead I make lambda be a value that's close to 0, then this term dominates, and I get nice sustained activity after the input goes on, but it doesn't follow the input very well. Okay? In fact, this thing is really simple to analyze. It's a shift invariant linear system. In signal processing, we would call it a recursive, sorry, not recurrent in the signal processing literature, a recursive linear filter with an exponential impulse response function. Okay? And you do a little bit of algebra right here, and you can turn this thing into this thing in which we have a new time constant here, which is the original time constant divided by lambda. So that's how you can see that lambda controls the effective time constant of the low-pass filter. Okay? Now what we kind of want, just to get started, even just to get sustained delay period activity before we get to manipulation, we want this part here, but we want the maintenance from there. And so the answer is obvious. You just change the value of lambda. Okay? And so that's the starting point. We're going to generalize from that. So that's one of our gates that plays a role that's analogous to the update gate in an LSTM. So here's what an organic looks like. Okay? Again, I have a vector of output responses y, I have a vector of input responses x, and I have, instead of the lambda, I'm replacing the lambda and the 1 minus lambda with these two things, an a and a b. And if a is equal to b, right, you can just do the algebra in your head, this thing is going to be 1 minus that thing when a is equal to b. Okay, so when a is equal to b, this is the same as the previous form. I'm doing it with 1 over 1 plus in each case, because it's actually convenient to work with. Now I only need to have things be, before the lambda had to be clamped between 0 and 1. Now it just has to be rectified bigger than 0. We're also going to see an idea later on about how this maps directly onto a biophysical model of a pyramidal cell in cortex. Okay? All right. So that's the setup there. The output response depends on the input drive and the recurrent drive. Again, the input drive is a weighted sum of the input. The recurrent drive is a weighted sum of the output. We also have a readout matrix here, okay? So that, for example, in the delayed Saccade task, I can look at the delay period activity of all the neurons and read out from it where the target was, okay? And that's also a matrix here that's going to be filled with particular values, and the particular values we fill it with are actually going to depend on the weights and the recurrent weight matrix for particular mathematical reasons. What do the weights do? Well, following the standard trick from the AI literature with LSTMs, the two gates, A and B, or modulators, A and B, are each a weighted sum of the inputs and the outputs in general. Okay, but the examples I'm going to give you are really simple ones. And then they have to be half-wave rectified. Okay, so they have to be bigger than 0. The superscript plus sign here means some kind of rectifying output, not linearity. Okay, here's a simple example of the delayed Saccade task. I'm using a weight matrix that's the same one that I illustrated a few slides ago, in which there's local excitation and recurrent inhibition from farther away. So this is what the recurrent weight matrix looks like right here. Oops, sorry. I hit the wrong button. Right here, okay? Here's what the input looks like. Target flashed over here and down there, okay? This is what the input drive looks like after taking a weighted sum of that to give you those Z values. Here's what the update gate and the reset gate look like, or the two modulators A and B. Notice that they're both turned on here at the beginning. That's the same as making the lambda value close to 1, so the output follows the input. And then before the target goes off, they get shut down to 0 so that the recurrent drive now dominates, and the responses stay sustained throughout the delay period. Then at the end, the A gate comes back on again to shut things off. Okay? So basically you have two control knobs here. One controls the time constant of, you know, when those modulators are held to fixed values, that's just changing the time constant of the low pass filter. And the other one is controlling the recurrent gain of the recurrent drive, which we can shut off by turning that modulator on. Okay, so that's a pretty simple example. We can think through how to analyze its behavior. First of all, let's look at what the response dynamics look like during the delayed period. So here we have, you know, the same equation again, and now I'm just simplifying it to a recurrent weight matrix that looks like this. Okay, so it has 3 non-zero weights along the diagonal. One of them is equal to 1, one of them is slightly less than 1, and the other one's slightly more than 1. And those of you who know about dynamical systems already know what's going to happen here. So the first value in y, there's 3 entries in the vector y, will get multiplied by that over and over again, and it will get smaller and smaller over time during the delay period. The one that's equal to 1 will stay constant over time, and the one that's bigger than 1 will increase over time, eventually increasing without bound if you let it go for long enough. Okay? Now this idea generalizes to an arbitrary case in which you have an arbitrary set of weights in that recurrent weight matrix with one little mathematical trick, which is you need to think about it not in terms of the weights themselves, but the eigenvectors and eigenvalues of the weight matrix. Okay? And in the particular case that I showed you here, there are exactly 2 eigenvalues that are equal to 1. And I scaled the weight matrix so that all the other eigenvalues are less than 1, so that all that matters is the eigenvectors corresponding to those 2 eigenvalues. And those are the ones that determine all of the dynamics in here. And in fact, those 2 eigenvectors is what I picked for both the encoding embedding matrix and for the readout matrix. And by doing things that way, the input gets projected onto that space spanned by those 2 eigenvectors. That's the information that's held through the delay period, and I can use that readout matrix to pull out the target location at any moment in time. Okay? So in this case, I'm calling the representational dimensionality is 2. The whole thing behaves like a 2-dimensional continuous attractor. We know that because of this eigenvector-eigenvalue decomposition. And by construction, I chose the embedding weights and the decoding weights to be the same as those eigenvectors. Not going to go through the next slide, which is just a simple little derivation to show you that by choosing the embedding matrix and the readout matrix to be that, the estimate you get by reading out at any time during the delay period is equal to the target location that you plugged in the first place. All right, that's a really simple example. Here's a slightly more interesting, slightly more complicated example that's kind of an extension of the delayed Saccade task. It's now going to be a delayed double Saccade task, which works like this. You're holding fixation here. There's a pair of targets that are flashed. After the fixation point goes off, you're going to have to make eye movements in sequence, first to this target and then to that target, but they're no longer on the screen. Now, the one little bit of additional information you need to know, for those of you who aren't neuroscientists, is that the brain codes for these eye movements in an eye-centered or retinotopic coordinate system. Okay? As illustrated by these 2 red lines here. When the targets are first flashed, That's the amplitude and direction of the eye movement you'd need to make to the first target. That's the amplitude and direction of motion you'd need to make to the second target. But as soon as you've made an eye movement to the first target and you want to make that second eye movement, this information is now out of date and would take you to the wrong place. So somehow the brain needs to update, that's a simple form of manipulation, what that planned eye movement is, taking into account that in the meantime the eyes have moved to a new location. Okay? Fortunately, the brain is set up to provide you with that information. The signals that are sent to control the eye muscles to make the eye movement, a copy of that signal is sent back to the brain. It's called a corollary discharge or an efference copy of the motor command. And the idea is that you somehow need to, while the eyes move from here to here, the circuits in the brain that want to plan the next eye movement need to integrate the original Saccade plan, this one, with the actual eye movement that's taking place, integrate those two things in order to update what the second planned Saccade will be, this dashed line right here. Okay, so you can program, there's a simple example, I just did all this by hand. This is what the recurrent matrix or weight matrix looks like. It looks like two copies of the thing we had before, just stacked next to one another. Here I'm showing you time courses of two target locations, one that's over 1 and up a half, another one that's over 1 and down a half. This curve here is the corollary discharge. When you make the first eye movement, you go over 1 and up a half. When you make the second eye movement successfully, you go over not at all and down 1 step. Okay? This is the input drive, which we get same way as before. I take the eigenvectors of the recurrent weight matrix, and I use that as my embedding matrix to take now 4 numbers from the input into this now 16-dimensional space. This is what the modulators look like, the A and the B, just as before we turn them on, so that the output neurons are encoding the locations of the two targets. And just as before at the very end of the trial, we flip the A modulator back on to shut everybody off. But the interesting thing that happens in the middle is we flip on the B modulator for a little period of time during each of the eye movements. And that lets the corollary discharge signal come through, which naturally integrates it with the saved kind of stored maintenance of the target positions. So you're seeing right when this happens, things shift around. Right when that happens, things shift around. And the bottom two curves, for those of you who can see it, are the readout from this of the simulated planned eye movement, which here is over 1 up a half. Then after the first eye movement, there's nothing left to read out from the representation of target 1, but this guy has changed from over 1 down a half to not over at all down 1, and likewise for the next one. So it acts like, in this case, a full integrator, not a leaky integrator, combining information from the corollary discharge with the remembered location of the second target. So this is a very simple example of this kind of long-term dependency of combining information that was presented to you before with information that's happening right now about your eye movement. All right, so you've seen recurrent, we got that. We've seen neural integrator, you've got that. You've seen gated, we've got that. So we're missing the oscillatory, and that's coming next. All right, here's another simple example. Here's a recurrent weight matrix. Now we have 100 neurons. These weights are all 0, these weights are 1, and there's a 1 up here. This looks like an identity matrix, but it isn't. All the ones are shifted down off the diagonal by 1 step. So this is like neuron number 1 becomes active, and it says to its partner number 2, you go next, and number 2 says to number 3, you go next, all the way down to 100, that comes back to number 1 again. And this has been called in the neuroscience literature dating back certainly to the 1980s by Moshe Abeles, a Sinfire chain, a kind of trading off of information from one to the next. Now, the cool thing is that when you do the eigenvector decomposition of this, you find that the eigenvectors and eigenvalues are complex valued. And there are 2 of them that have eigenvalues with real parts that are 1, and the other ones have eigenvalues that have real parts that are less than 1. And so we still have a representational dimensionality of 2, but now we need to deal with not 100 neurons, but 200 neurons. Because there have to be 100 neurons to code the real parts of these complex valued numbers and 100 neurons to code the imaginary parts of these complex valued numbers. And the weights, there's not 100 by 100 weight matrix in the embedding matrix and so on. There has to be 2 of each of those, a real part and an imaginary part. 2 synapses, one that holds the real value part of the weight and one that holds the imaginary value part of the weight. And lo and behold, what comes out of this thing is oscillations. And that makes perfect sense if you know about the dynamical systems idea, that when you have these complex valued eigenvectors and eigenvalues, the real part of the eigenvalue determines whether it stays flat if it's 1, goes up if it's bigger than 1, or down if it's smaller than 1, and the imaginary part determines the frequency of the oscillation. Okay? And in this particular case, I have 100 neurons, each of which had a tau, a time constant of 10 milliseconds, so the periodicity here is about a second, almost exactly a second. You're seeing in the top row the real part of the output responses, in the bottom row the imaginary part of the output responses. And the really cool thing is that to do the readout, you do exactly the same thing as before. You take those same eigenvectors, and at any moment in time, you can just take a dot product between the responses of the 100 neurons, their complex valued pairs of responses, and those 2 complex valued eigenvectors. That's just some multiplies and adds, and you get the target position back, same as before. Okay? So one of the messages here is, but don't be freaked out by modulations of activity during a delay period. Okay? It can still be perfectly well maintaining information in a way that's essentially constant over time. You just have to think about it in this, now complex valued space to get the complex dynamics. So now let's just go crazy with it. So I made a 100 by 100 weight matrix filled with complex values. Subject randomly chosen numbers, subject to the constraint that 10 of the 100 dimensions here have real parts of the eigenvalues equal to 1, and the other 90 are less than 1. I scaled the weight matrix to make sure that none of them were bigger than 1, and randomly chosen imaginary parts. And we do exactly the same thing, the same kind of simulation. You provide an input, you project that through the embedding matrix, which has none other than the 10 eigenvectors that are, that have real parts equal to 1, and then you change the gates. And instead of getting constant delay period activity, you get what looks like, if you were a neurobiologist, a mess. There's all kinds of stuff going on here. Neurons, responses are going up and down and wiggling around, and they're all doing different things. But I can read out the kind of simulated now 10-dimensional equivalent of the eye position in exactly the same way, just by computing a weighted sum with that same set of eigenvectors. Okay, no problem. All right. And then I was homesick with the flu a couple weeks ago, and I was watching the Olympics, and I saw this, a backside double McTwist 1260, okay, which we cite Shawn White 2018. And I thought, how does he do that? There's he hits the lip of the half pipe, and there has to be some kind of motor preparation state, and then he just hits the go button, and there's this ballistic sequence of complicated sequence of movements that has to take place, right? There's almost no time for any sensory feedback. You get to spot the landing and make a little bit of adjustment so that you hopefully don't kill yourself, right? But it's a pretty complicated play out of motor activity. And I got to thinking about it, here I am talking to you now, and I think it's actually pretty similar. I'm loading up some kind of cognitive state, and I hit the go button, and out comes a whole sentence, and I'm not even sure what word is going to come next. And usually it actually comes out right, okay? So we do this all the time, okay? You don't have to be Shawn White to do this. And I thought, okay, so not too bad. So I thought, okay, well, maybe we can just use the same tool. So the only difference now is that instead of making the readout matrix be set up to recover the input, I can choose an arbitrary readout matrix, and then I can compute weighted sums of these complicated dynamics. So here's a little simple example just to illustrate the idea, not really solve a problem. So if I take that very same random-ish weight matrix. Remember, I scaled it and set it so that 10 of the eigenvalues have real parts 1 and the rest of them less than 1. Take that exact same thing, and I provide an input which is equal to the first eigenvector. And then so you set up a state, and then I change the gates, setting the modulators A and B to 0, and I get all this stuff, real part, imaginary part. Notice that they all have the same frequency. That's determined by the imaginary part of that eigenvalue, but they all and they don't decay or grow in amplitude. That's because the eigenvalue has a real part equal to 1, but they all have different amplitudes and phases, and that's because of the corresponding elements of the corresponding eigenvector. Okay? If I hit it with the second eigenvector, well, I get different dynamics. It happens to have a lower frequency, and because this is a shift invariant linear system, if I provide an input, which is the sum of those two eigenvectors, I get this, and if I literally sum this plus this, I get that. Okay? All right? So the readout now can be any weighted sum, and this is just with 2 dimensions. In that particular weight matrix, I have 10 dimensions to work with, but I could have 100. I could just have all 100 of the eigenvalues have real parts equal to 1. And if I had 1,000 neurons, I could have a 1,000-dimensional continuous attractor space in which I can explore different dynamics. Okay? It all depends on what the weights are in the weight matrix. Now, I promised to get to the neurobiology, and I'll just do this quickly. One of the things we learned a century ago from Cajal and others is that is the idea that there has to be a connection between the structure of elements of the nervous system, like neurons, and their function. And one of the weirdest neurons, I'm trained as a computer scientist, so I can say, one of the weirdest neurons is the one that's actually one of the most common in cortex, which is a pyramidal cell. And it has this funky, crazy structure in which there's a cell body here and 2 separate branches of the dendritic tree called apical dendrites and basal dendrites. And I kind of thought, well, okay, wouldn't it be just neat if, like, the recurrent drive went to the apical dendrites and the basal drive went to the and the input drive went to the basal dendrites? And so I decided to draw out a biophysical electrical circuit model of a pyramidal cell. It has 3 compartments, one for the soma, one for the apical dendrite, one for the basal dendrite. Within each compartment, there's a variable conductance resistor, which is going to be the synaptic input from the gates, A and B, and a current, which is a variable current, which is the recurrent drive and the input drive. And I need to finish now. You look up Kirchhoff's laws, do a little bit of algebra, and you get something of the right form, 1 over 1 plus stuff. And the other piece of it is that the modulators themselves, we're hypothesizing, are computed in a particular structure in the thalamus, which we know has these loops with prefrontal cortex that affect the prefrontal sustained activity. I can apply the same stuff back in visual cortex. There's lots more to do, including stacking them, which can give you deep nets as a special case. Learning the weights is important. Finally, very quickly, implications for neuroscience. Working memory is much more than short-term memory. Don't be freaked out by complex dynamics. We have some experimentally testable predictions, and I think there are some implications for AI. Go complex. Simple harmonic motion, like my motion right now, body motion, speech, music, all simple complex, simple harmonic motion, using basis functions like damped oscillators may win over what effectively LSTMs do, which is approximate signals as being piecewise constant. You can make these things stable by scaling the weight matrix so that the eigenvalues don't get bigger than 1. And because we can implement it in an analog circuit, you might be able to build a neuromorphic chip to do it. And that's that. And I have 30 minutes here out of 40.
I just go with the light on the timer.
Oh.
Okay, so we have time for some questions, and I think we have people handling mics. So if you have a question, just raise your hand and wait for them to come to you. So I have a question to kind of get the ball rolling. So one comment you made a moment ago was that the weights are everything. So can you talk about the kind of different timescales for which the weights might be selected?
The different timescales. So there's two different ways to think about timescales here. One is the frequency of the oscillations, which is presumably at a pretty fast time scale. The other one is controlled by the time constant of the neural integrator, which can be quite slow, right? And remember, we're controlling the neural integrator just by changing the gain simultaneously on the input drive and the recurrent drive. So the way that I think about all of this is we've done some experiments to show that there's a hierarchy of timescales of processing, with longer timescales kind of further forward and shorter timescales in sensory areas of the brain. And I would imagine the same is true in motor cortex. As you get closer and closer to motor control, you're going to be at shorter and shorter timescales. My guess would be that would go along with both having higher frequency oscillators, higher frequency basis functions, and also a range of time constants that's shorter.
Other questions? Just hang on and wait for the microphone.
As far as I understood, basically all the weights in your neural network were hand-picked, so you did not learn them, right?
That's correct.
And is there any way how you could learn them?
That's a great question. I think that's a really, in fact, central and critical issue to go after. Algorithms for learning the weights. I see three options. One is good old backpropagation. The problem with that here is that you would need to have supervised training signals that are sampled at every time point. Okay, so that would be fine for some things. Like we could use this as a model of behavior in people or in animals, in which we kind of know the task structure and can create by hand what the output is supposed to be at every time point, right? Or measure continuous behavior or something like that. So it's good for that. For AI applications, rarely will you have a continuous time training signal. I see two other options, one of which is the continuous time generalization of reinforcement learning, which is called adaptive dynamic programming. Some of you probably know that there's a continuous version of the Bellman equations, and there's a whole little subfield of control theory and systems engineering that keeps chugging away on this, and I'm curious to learn more about it. I'm a newbie at that. The third idea, which was something that was that I wrote about in last year's paper, in the Proceedings of the National Academy paper from last year, and there's another idea that's sort of floating around in AI, but I think there's a lot of room to do research on it, is to train the weights via prediction error. So conceptually, the idea is that each neuron is essentially projecting forward in time what it thinks its response should be a little while later, and it can compare that with what its response actually is and use that as a learning signal to change the weights. Okay, there's some things that are really hard about that, right? The simplest one, Eero Simoncelli, who might be here, pointed out to me a couple years ago. The simplest way to optimize that is to make all the weights be zero. Then all the responses are zero, and you can predict things perfectly. So that's a bad degenerate solution, but that illustrates why it's hard. But I think it's fundamentally interesting. I think using the statistics of the world, the way the world changes as you interact with it, to do a prediction error-based approach to learning, is something that should be a priority for thinking in both fields.
Thanks for your talk. So I have I have a follow-up on the hierarchy issue, and it's great to hear you're thinking about using reinforcement learning or prediction error learning for the learning aspect. One thing I was wondering about is for the hierarchy, for the timescale hierarchies to have brain-like properties, should there be a particular relationship between the imaginary parts of the different eigenvalues? In order to have the right timescales or similar timescales to different parts of the cortex?
Yeah, it could be. I mean, so also in last year's paper, I wrote a lot about one of the big things that I focused on in that paper is how you can have both feed forward like a deep net and feed back connections, and use the slow time scale representation high up in the hierarchy to constrain, kind of like a prior, in some cases exactly a prior, the faster time scale processing. It's not clear to me how much of that time scale work is being done by the difference in the time constant versus the difference in essentially the frequency of the oscillators. And you know, one of the things I want to do with this is take it to some real AI, you know, take it to some real AI applications. For example, speech or human movement, and try to gain some insight from you know, learning weights that work well to solve those kinds of real world problems with real data, try and gain some insights about how that hierarchy might play out. I mean, it should be obvious, but I'll say it anyway. It's easy to stack these things, right? So you can take one of these organics and have its input be the outputs of, you know, one or more other organics, and then if you make the embedding matrix convolutional, and you set the modulators to be bigger than 0, then you have a deep net as a special case, right? So you can stack them in the same way you would a deep net. And it has the computational advantage that the only real nonlinearity in sight is a rectifying nonlinearity, in the same way that rectified linear units have kind of enabled deep nets to get really deep.
So if you're at the back and looking for a seat, there's a few more seats closer to the front on the side there. And we've run out of time, so let's thank David again.